Hello and welcome. I'm Dr. Pauline Fu. In this video, I will talk about relationship between two variables. Specifically, I will talk about scatter diagram and correlation. By the end of this lecture, you will be able to draw and interpret scatter diagram. And you will be able to describe the properties of linear correlation coefficient. And I will give you the formula to calculate linear correlation coefficient and explain the interpretations. And we'll discuss whether a linear relation exists between two variables. Finally, we will explain the difference between correlation and causation. So let's look at an example. This example is about a drilling, okay? You are drilling a stone. So one variable is depth at which drilling begins. The unit is in feet, that is x. So the depths, those are my x. The other variable is the time to drill 5 feet. Time to drill 5 feet, that is y. So this horizontal line is y. Time to drill 5 feet. Okay. So you recorded the number. For example, the first number 35 means at 35 feet, you drill 5 feet. The time span is 5.88. Okay. Next, number 50. At depth of 50 feet, the time to drill 5 feet is 5.99, etc. And we call this x variable is explanatory variable or predictor variable. So in the following lectures, I will use these terms interchangeably. Explanatory variable, predictor variable, x variable, they all refer to this horizontal axis, okay, horizontal axis. And y variable, we also call response variable or y, refer to this vertical axis. So how do we get the data from here, the table, to a diagram? You can use Excel. So this is the data, okay. So in this data, you highlight the data range, including the labels. And then you go to insert, scatter plot. See, you'll get this scatter plot, okay? So this is how do you use Excel to create a scatter plot based on data set. Hold on, yes. So based on this example, we'll draw general conclusions. Generally speaking, there are various types of relations in a scatter plot. always remember the X represent explanatory variable and Y represent response variable. If you get this kind of scatter plot, it is a linear scatter plot. And in this linear plot, when you increase X, Y also increase. So we call it is a positive linear relationship. This graph is also linear, okay? But when you increase X, Y decrease. So that is the negative linear. Beautiful sound today. And sometimes when you draw the scatter plot, you get this like parabola. And this is a non-linear relationship between explanatory variable and the response variable. Other kind of non-linear, you have this, okay? This like this, non-linear. And you have no relationship at all, okay? Between explanatory X, variable X, and the response variable Y. So this is the various types of relations in a scatter plot. In a scatter plot, we will introduce a very, very important terminology, linear correlation coefficient, or Pearson product moment correlation coefficient. We use small letter r, sometimes capital letter R. Okay. The linear correlation coefficient measures two things. One is the strength between X and Y. The other is the direction between X and Y. The bigger the number, the stronger the relationship. And when you have a linear correlation coefficient is a positive number, that is the positive relationship. If the linear correlation coefficient is a negative number, it is a negative relationship, okay? So that is a linear correlation coefficient describe the strength and the direction of linear relation between two variables. Remember, we have to distinguish between population and sample. If the linear correlation coefficient refer to population, we use Greek letter rho. Greek letter rho represent population correlation coefficient. And if the linear correlation coefficient refer to sample, we use small letter r or capital letter R represent the sample. For calculation purpose, I will only introduce the formula for sample. How do I calculate linear correlation coefficient for sample? This is the formula. N represents sample size, how many data in the sample. Okay. X bar represents the mean of the explanatory variable, the mean of X. Okay. Explanatory variable is X. And the Y bar represents the mean of response variable. Response variable is a vertical line Y, the mean of Y. Sx is the standard deviation for X. Sy, standard deviation for Y. So now let's do the calculation for our example. This data set here. The question is calculate linear correlation coefficient for this data. calculate linear correlation coefficient for this data. Use the formula, okay? Use the formula. So I'm going to pull out my Excel, okay? And move this graph on the side. So this is the original data. What we need to do, I'm going to insert, we need some space. I'm not going to, I'm going to delete some data. I need space to calculate X bar, Y bar, SX, SY, okay? So we need to calculate the mean and the standard deviation for, this is my X, see the X, this is my Y, okay? So what is the mean for X? You just need to do the average, okay? So equal average this number. So the average is 126.25 feet. Okay. Do the same thing for Y. I just copy down the formula. The average for Y, 6.98. 6.98. Okay. I'm going to keep just 2 decimal places. Maybe this one, okay? No, maybe 4, okay? To maintain accuracy. All right, so I figured out this. 126.25 is X bar, and 6.9858 is Y bar. Okay. So we also need standard deviation. So standard deviation for X, STDEV dot S means sample. Standard deviation is 52.22. And copy down the formula. Standard deviation for Y, 0.78. So I'm going to keep just 4 decimal places. Okay. So I have X bar, Y bar, SX, SY. Next, how do I figure out this R? Okay. To figure out this R, I need to calculate this. Okay. So I'm going to calculate what is Xi minus X bar divided by Sx. Try to make the font bigger. Okay. Xi minus X bar divided by Sx. I also need to know Yi minus Y bar bracket divided by Sy. So I need to calculate this. And then I have to multiply this term together and add them all, divided by n minus 1. Okay. All right, you ready? All right. So equal X minus X bar. This is my X. I use cell reference because I want to copy down the formula. Next time X becomes 50. Next time X becomes 75. So X is changing. That's why I use cell reference. So this is my X minus X bar. This is my X bar. Because X bar is fixed for all the X. So I need to translate this X bar into absolute cell reference. $C, $15. Okay. So that everybody minus this 126.25. Okay. So anyway, this is my X minus X bar divided by Sx. the standard deviation. The standard deviation is also fixed for all the x. So I also need absolute cell reference $C, $16. Okay, so press enter. Oops. And this is x minus x bar divided by Sx. You can verify on your calculator. Now I'm going to do y minus y bar. Okay. This is y minus y bar. This is y bar. Again, y bar is the same for all the y. So I need to use absolute cell reference. Oops. This is $D, $15. And divided by standard deviation for y. Again, use absolute cell reference. $D, oops. When you use PC, you can press just F4 button. Here I have to add manually. $D, $16. Okay, so double check everything all right. Now I'm going to double check this one. This one I miss $sign here in front of 15. Okay, $C, $15. Okay, and now I'm ready to copy down the formula. Select these two cells. Okay. But before we do that, double check. This is the formula I entered. Okay. And this is the formula I entered. So now copy down the formula for all the x and y. Okay. And you have to multiply these two items together. You have to multiply them together. So where is my Excel? Okay. Now you have to times, okay, I just use this represent multiply. This number multiply this number, okay, equal multiply and do the same thing for all the cells. So I finished multiply and then this sigma means add them all, okay, add them all. Do the addition. So there is a sigma, means sum all these numbers together. That is the sigma. Okay. And after you finish that, you have to divide it by n minus 1. So how many data here? Okay. What is the n? You can use the count function. Equal count. From here to here, how many numbers? 12. Okay, so n minus 1 is 11. Okay, so what is the linear correlation coefficient R? Linear correlation coefficient R, it is just the ratio of this sigma divided by n minus 1. Okay. So I get 0.7728. That is my linear correlation coefficient. Hope you will go through this process by yourself using either Excel. The calculator is very many steps. I strongly suggest you repeat this procedure to do it in Excel to see if you can come up with the number 0.7728, and this is a positive number, and this number smaller than 1. So that is the formula for calculate linear correlation coefficient. Next, we'll discuss the properties of this linear correlation coefficient. Linear correlation coefficient always between -1 and +1. If it is equal to positive 1, there is a perfect relationship between x and y, means all the x and y, this is my x, this is y, all the x and y are lining up in the straight line. And when you increase x, y also increase. And when you have r equal to negative 1, r equal to negative 1, again, all the x and y lining up on the line, but in the negative relationship, downward in straight line. And if you have the closer the r to positive 1, the stronger the relationship, the positive relationship between x and y. And the closer the r to negative 1, the stronger the negative relationship between x and y. And when r close to 0, it does not simply mean no relation, but it is just non-linear relation. It may have other relationships, for example, parabola or polynomial, polygon. Okay? The other property is the linear correlation coefficient does not have unit, Last one for the property of linear correlation. If an observation that does not follow the overall pattern of the data, it could affect the value of linear correlation. Because of this reason, we say linear correlation coefficient is not resistant, because an extreme number, very big number, or very small number could affect the value of linear correlation coefficient. So this is the diagram represent the properties of linear correlation coefficient. If you have r equal to 1, perfect relationship between x and y, so this is x, this is y. And if you have r equal to 0.9, that's close to 1, they have a stronger relationship between x and y. Stronger relationship between x and y. And when you increase x, y also increase. And this example is when you have r equal to 0.4. When you have r equal to 0.4, okay, there is a non-linear positive, there is a moderate positive relationship between x and y. So any value may be between 0.4 to 0.6, moderate. Above 0.6, like this, strong relationship. And here you have r equal to -1, okay? Perfect linear relationship between x and y, but it is downward negative relationship. When you increase x, y decrease. And this diagram, when you have r equal to -0.9, so when you increase x, y decrease downward, and pretty strong negative relationship. And r equal to -0.4, moderate negative relationship between x and y. You see, compare this diagram with this diagram. This one is stronger, and this one is moderate. And this one, if you have r close to 0, non-linear relationship. Non-linear relationship. Maybe have other relationship. Again, this one is also r close to 0, no linear relationship, but may have a parabola, okay, quadratic relationship. All right. So we already did this calculation. We come up with the same result. Maybe I want to copy just some formula, but okay, that's fine. I use cell reference. So next, let's ask our question. How do you know whether there is a linear relationship exists between two variables without using scatter graph? How do you know without graph? Just giving you the data, okay? And you go through the 3 steps. Step 1, you figure out what is the absolute value of the correlation coefficient. Why we ask for absolute value? Because the linear correlation coefficient could be positive, could be negative. When you have a negative linear correlation, we need to take absolute value, okay? Absolute value. So that is the step 1, take absolute value of linear correlation coefficient. Step 2, find the critical value in this table, critical value. So this table has 2 columns. The first column is the sample size n, okay, sample size n. The second column is the critical value. This column is the critical value. For example, in our example here, we know n equal to 12, sample size equal to 12. When sample size equal to 12, what is the critical value? So look at here. When sample size equal to 12, critical value 0.567, 0.576. So found the critical value. And step 3, compare step 1 with step 2, okay? If the absolute value of correlation is greater than the critical value, we say there is a linear relationship between 2 variables. And if the absolute value of correlation is smaller than the critical value, we say there is no linear relationship between 2 variables. Okay, so now let's use these 3 steps to do our example here. The question is there a linear relationship between x and y? This is my x, this is my y. Okay, step 1, find linear correlation coefficient and take absolute value. It is a positive number. The absolute value is itself. Step 2, based on sample size n equal to 12, found the critical value 0.576, okay, 0.576. Step 3, compare step 1 with step 2, okay? And step 1, we got 0.773 absolute value. This value linear correlation coefficient greater than critical value 0.576. When the absolute value of linear correlation greater than critical value, we conclude there is a linear relationship between x and y. In this case, there is linear relationship between the depth and the time. Okay. So far we talked about the scatter plot. We calculate the linear correlation coefficient, and we also test if there is a linear relationship between two variables. Next, we will explain the difference between correlation and causation. Okay, so we are going to use example, okay, between correlation and causation. According to data obtained from the statistical abstract of the United States, the correlation between the percentage of female population with a bachelor degree and the percentage of births to unmarried mothers since 1990 is 0.940. I repeat the data. The correlation between the percentage of female population with a bachelor degree and the percentage of births to unmarried mothers is 0.940. Looks like a very high correlation. But does this mean that a higher percentage of females with bachelor's degree causes a higher percentage of births to unmarried mothers? By common sense, of course not. Why not? Because the correlation exists only because both percentages have increased since 1990. Okay. It is this increase caused the higher correlation, not the two variables themselves. It is just the increase. In general, those are the time series data. Time series data may have higher correlation because each variable is moving in a specific direction over time. This direction could be two variables move together, move up or move down together. It could be one variable is up, the other variable is down. So because of this reason, and when we use the observational data, we cannot claim a causal relation exists between two variables. In order to claim a causal relation exists between two variables, we have to use a designed experiment. That is out of this topic. Okay. And also in explain the difference between correlation and causation, we have to be aware of another concept, lucky variable. A lucky variable is related to both explanatory variable. Remember, X is the explanatory variable. Okay, and remember Y is the response variable. For example, ice cream sales and crime rates have a very high correlation. Does this mean that local governments should shut down all ice cream shops? No. The lucky variable is temperature, because temperature relates both ice cream sales and crime rate. As air temperature rises, both ice cream sales and crime rates rise. So temperature is a lucky variable. Let's take another example to explain lucky variables. This data is about number of callers per week, okay, and bone mineral density. So because callers tend to replace healthier beverage, and callers contain caffeine and sulfuric acid, researchers Catherine Tucker and associates wanted to know whether cola consumption is associated with lower bone mineral density in women. This table lists the typical number of cans of cola consumed in a week and the femoral neck bone mineral density for a sample of 15 women. The data were collected through a prospective cohort study. So again, this is observational study, okay? Remember, observational study have the cohort study, case study, okay, and the cross-sectional study. So this belongs to a cohort study over a longer period of time. So what is the question here? Can the author conclude that an increase in the number of colas consumed causes a decrease in bone mineral density? Identify some lucky variables. So first step, let's calculate linear correlation coefficient R using the same method, okay? You can calculate linear correlation coefficient, but here I will introduce a new method. So this is the data. How do you use Excel without use the formula? Directly get linear correlation coefficient R. This is our data. So I will put the result maybe here. What is R? You type in equal COR REL co-real, then opening bracket. This is X, and this is Y. And you get this number here, okay? This is how you calculate the correlation coefficient using Excel. Just use Excel equal co-real, COR-REL. And then you select X, comma, select Y. Okay. So we have a higher, this one is a stronger, looks like stronger relationship between X, by the way, this is my X, this is my Y. But as a matter of fact, the X has nothing to do with the Y, okay? There is a lucky variables. So what are the possible lucky variables? If a person smokes a lot, 20 cigarettes a day, or the person drink a lot, alcoholic, or the person does not have an active lifestyle, do not do activity a lot, those might affect the bone mineral density, bone density. Okay. And maybe the social economic status also affect the bone density. So those are the lucky variables. This is the scatter plot, okay? So by the way, how do you create a scatter plot? You just highlight this data and go to insert scatter plot, you get this data. So that's all for this video. In summary, what we did in this video, we introduced how to use Excel to draw scatter diagram. We described the properties of a linear correlation coefficient. We also interpret the linear correlation coefficient. And we use 3 steps to test. How do I know there is a linear relationship between 2 variables? Finally, we explain the difference between correlation and causation. I hope you enjoyed this video. Thanks for watching. Have a great day. See you next time.